This slideshow will explain how rocks melt by the process of decompression melting, which is one of the three main ways that rocks melt. Now, before we begin, let's think about how we normally imagine the process of melting to occur. So here we have a portion of the phase diagram, right, with temperature vertically up like this. Okay, so up is higher temperature. And the solidus line here represents the temperature, which marks the transition from a field of all solid into one in which the rock is partially melted. So above that solidus line, there's some amount of liquid present as well. And we start with a composition at a temperature indicated by the yellow dot. So because this yellow dot, this rock at this temperature, lies within the blue field of all solid, we know that it's not melted at all. And if we want to melt this rock, we know what to do. We simply raise the temperature of the rock until it crosses the solidus temperature, and at that point it begins to melt. Simple as pie, right? If you want to make something melt, you heat it up. But notice that all that's really required for the rock to melt is that its temperature exceed the solidus temperature. And there are actually two ways we can make this happen. We can do just what we did and cause the rock's temperature to rise, or we can do the opposite. We can start with a composition like this at a temperature as indicated by the yellow ball. And now we're going to keep the temperature of the rock constant, but let the solidus temperature fall. So as the solidus temperature falls, the rock, which isn't changing in temperature at all, which is staying at the same temperature, once again finds itself at a temperature above its solidus temperature, and that's all that's required for it to begin to melt. So in other words, we can either raise the temperature of the rock, or we can lower the solidus temperature. We get to the same place regardless, which is the rock is above its solidus temperature, and so it begins to melt. Now, if we look at the phase diagram again, we can see the conditions under which that can happen. How can we cause the solidus temperature to fall? And if we notice, we see that the solidus temperature is related to pressure. So that as we increase the pressure, as we go down here, increasing the pressure, the solidus temperature increases. So that if we have a process in which the pressure is decreasing, what we would expect to see then is that the solidus temperature during that process will be falling, and therefore that is the mechanism by which we can lower the solidus temperature and cause a rock which doesn't change in temperature to actually begin to melt. So this is, in other words, what we can do. We can start with a rock at a constant temperature and keep the temperature constant. As the pressure decreases, the solidus temperature falls, and the rock will find itself above the solidus temperature. In other words, it will begin to melt. So let's imagine how this actually happens now inside the Earth. So here I've got a cross section of the Earth with pressure increasing downward, pressure and depth increasing downward. And I'm going to imagine a big blob of rock that lies within the asthenosphere. So it lies beneath the lithosphere. It lies within the portion of the mantle that can flow, and in particular this blob of rock is going to flow upwards. It's going to rise, and as it rises the pressure on it will decrease, and as the pressure decreases the solidus temperature will decrease, and ultimately it can possibly melt. Now, what kind of conditions does this represent? Well, this is exactly what happens, for example, at mid-ocean ridges, where the plates are diverging, and as they diverge, they induce an upward flow of rock within the asthenosphere that's doing exactly what I just described. It's asthenospheric rock that's rising, and as it's rising, the pressure is decreasing, and as it's rising, the pressure is decreasing, and the solidus temperature is decreasing. This also happens at hot spots, right? These are anomalously warm regions of the asthenospheric mantle where plumes of rock are rising in the asthenosphere, and as they rise, once again, pressure is decreasing, solidus temperature is decreasing. So this process we expect to see happening at places like divergent boundaries above and hot spots shown below. Now, in order to describe exactly what's going on, we also need the phase diagram, because the phase diagram shows the relationship between temperature and pressure. So here's that same blob of asthenospheric rock shown over here in the cross section, and on the right hand side I've shown where it would lie along the geotherm in our phase diagram for peridotite mantle rock. Now, as this rock rises, which we showed happening on the left-hand side, its temperature might or might not adjust. And it depends on how quickly or slowly it's rising. As the rock is going to rise, right, as this rock rises, it's going to enter into surrounding mantle that's cooler than it is, because as you go up, right, the temperature, as described by the geotherm, decreases. Now, if the rock rises really slowly, what happens is there's enough time for heat to leak out of this big blob of rock, and it will equilibrate with its surroundings, and therefore, in terms of its temperature pressure position on the phase diagram, it will continue to lie along the geotherm. So if I imagine now a rock, this blob that's rising really slowly, as it's rising really slowly, it can leak enough heat, it can lose enough heat via conduction, that it continuously lies at a temperature and pressure that lies right along the geotherm. That's not going to produce melting, right? Because this rock maintains its position within the field of all solid. It doesn't cross the solidus, it doesn't begin to melt. Now instead, let's imagine a process where this blob of rock now is going to rise relatively quickly. What I mean by relatively quickly is on the order of how fast plates move, a few centimeters perhaps per year. Now although that seems ridiculously slow, in fact that's much faster than heat can diffuse or conduct out of this blob. If this blob is sufficiently large, as we sort of imagine it to be on the order of tens or hundreds of kilometers in diameter, then as it rises at a rate of a few centimeters per year, heat can't escape it fast enough. In fact, as it rises at that rate, essentially its temperature will remain constant. And under those conditions, its path on the pressure temperature diagram will be virtually vertical, that is isothermal. So as it's rising, its temperature is staying nearly the same because it can't shed heat fast enough, and yet its pressure, which is due to the weight of the overlying rocks, is decreasing. So this is exactly what we've got. This is the situation we have now that can lead to decompression melting. We have a large blob of rock within the asthenosphere that for some reason begins to ascend relatively rapidly. As it ascends, it can't lose heat by conduction fast enough to equilibrate itself with the surrounding cooler rock. And in fact, its temperature remains essentially constant. So its temperature remains constant, its pressure decreases, and therefore its position on the pressure temperature diagram simply rises vertically. And as it rises vertically on this diagram, it eventually encounters the solidus, right? It's going to eventually encounter and then ultimately cross this blue line, which represents the transition from all solid to solid plus liquid. And as it does that, then the rock will begin to melt. It'll partially melt. Those partial melts will become squeezed out and rise to the surface and produce some kind of volcanism along the surface. This is the process of decompression melting. Now remember one more thing, that the composition of rocks produced by partial melting, sort of first order rule of thumb, is that they are one step more silicic or felsic than their parent. So when the ultramafic rock of the mantle partially melts, it produces a liquid, a magma that's mafic in composition. So that magma that's rising up to the surface and emerging on the surface as volcanism will be mafic. That's why at typical mid-ocean ridges, here shown on the left, or at hot spots shown on the right, the typical magma produced by decompression melting that appears on the surface is mafic magma. Remember that at mid-ocean ridges, one of the great discoveries was that the rock was monotonously basalt, the mafic volcanic igneous rock. And the same thing tends to be true at hot spots in the oceans. For example, Hawaii, almost the entire Hawaiian Islands are made up of the rock basalt, the mafic igneous volcanic rock, which is produced by partial melting of the peridotite mantle. So both these locations, the mid-ocean ridges and the hot spots, produce a primary mafic magma as the ultramafic peridotite rock of the mantle melts as it rises, and as it rises the pressure decreases, and as the pressure decreases its temperature stays nearly the same because it's rising relatively quickly. And under those conditions, the solidus temperature decreases until the solidus temperature lies at a temperature lower than the rock, and the rock melts, and that's decompression melting.